being recorded.
So what do you want to talk about?
Well, I want to talk about very non-ambitious stuff because I started thinking about really ambitious stuff and I got really bogged down. And I blame you for that, for you asking in me email some provocative questions, which I interpreted in a very ambitious way. Really thought about it, really tried to write down stuff and did not finish. So instead, I'm going to try to do really unambitious stuff today. So let's think about those Coxeter diagrams that we have associated. I mean, basically, we have a pattern, it's an alleged pattern consisting of just 3 Coxeter diagrams. And perhaps the pattern doesn't really extend beyond that, but something extends beyond that. And we also want to understand what's going on here. So first of all, let's just draw these 3 Coxeter diagrams and remind ourselves of what they have to do with. I mean, we started thinking about what abelian surfaces and their, how do you pronounce it? Neuron-Severi groups.
Yeah.
And this led us to think about, in some strange way, this led us to think about these Coxeter groups. So, okay, yeah, I'll try this. I'll try using the pen. That meant that I had to actually step over for a second and get a pen that I forgot to get. So, okay, that goes there, this goes here. Try to turn this around. And yeah, I still don't have the bugs worked out. So which 3 Coxeter diagrams are these? These are the ones for, do we have names for these? We have names for these in terms of those hyperbolic, non-compact, what are they called? Hyperbolic.
Well, these are paracompact, which is some special kind of it's like a especially nice non-compact thing, I guess. But
yes, but there's something very nice about that they're just on the verge of becoming hyperbolic. They're one step past. Well, I mean, so paracompact paracompact ones in general, I guess these ones are one step past affine. That's what they are. You have an affine thing, and you go one step beyond that, and it makes it hyperbolic. The general definition of paracompact might be a little bit different than that. But that idea of going one step past affine, that's very relevant to us because these affine things are, these affine Coxeter groups are basically pictures of number rings, pictures of Voronoi tilings of number rings. So, okay, so let's see. So we've got, well, let's see. So these are all straight line Coxeter diagrams. And so one of them has, 3 dots and 2 edges. And these other 2 have 4 dots and 3 edges. And so we can just name the Coxeter diagrams by listing the numeric labels on the edges from left to right. And so one of them goes infinity 3. And one of them goes, let's see, 4, 4, 3. They all ended 3. They all ended 3. Right, right. So we're arranging it so that the affine part comes first. So just a plain infinity all by itself. That's an affine Coxeter. There might be, it's possible there might be some slightly different definitions of what an affine Coxeter group is. I'm not really sure about, but these ones really are affine. They're like flat. The geometry is flat rather than hyperbolic or spherical. So we have 4, 4, 3, and then we have what is it? Is it 633 or is it 363? It really does make a difference.
I'm pretty sure it's 633.
I think you're right. I think you're right. Yeah, that makes sense. And so being straight line Coxeter diagrams, these are, you know, sort of basically polyhedron type things. And you're just kind of saying, what are the numerical labels saying? They're saying how many polyhedrons there are, how many faces are at a corner of some kind, but corner could be like an edge or something like that. Let's see.
So the 6-3, let's see, I believe we should think of it as like hexagons meeting 3 at a corner.
That's right. That's right. And the 4-4-3 is squares meeting 4 at a corner.
Yeah.
Right? And the infinity.
Yeah,
Okay.
that's weird.
Don't tell me. Infinity. Okay, infinity comma 3. That is well, okay. So right. So we're really ignoring the 3. We're just doing the affine thing first, right? So it's just infinity. So that is do you have a description of that?
It's an infinity gon.
The whole thing is an infinity gon, right? I'm trying to think of how to describe the things that it's made out of. It's made out of bigons or something like that, right? Each Voronoi, you know, so these are the Voronoi cells of actual integers. So, you know, it's like 5 plus or minus 1/2 is one of the Voronoi cells. All right. So I'm trying to get this here, see if this works. Where did the, okay. Let me see if I can get this to work. Something actually worked there. You can see the screen?
Didn't do share screen, I don't think.
Oh, yeah, I gotta do the share screen first, right? That's the basic thing I forgot. Okay, I'll listen.
Yep.
Okay, and okay. Okay. So let's see. So we have let's see, green and blue and red. And then we have edges. And I guess we use the tradition of leaving the 3s unlabeled. You know, those are the vanilla edges, the unremarkable ones. But we'll write an infinity here. So you're telling me this is like a tiling of the Poincare hyperbolic disk or something like that by infinity gons. I mean, there's also a Poincare dual way to think about it, but okay. So one of the things I really want to try to do here is try to give explicit, see how easily we can come up, and you know, if we can't do it easily, then maybe we'll postpone it for homework. But see how easily we can come up with explicit generators for these dots in the Coxeter thing. So let's see. what's the green, blue? I should do it in, obviously I'm not doing it in Newton order here, but a yellow and red. And so what have we got? 6, well, I guess I'll do the 4, 4, that one first. And then we have this other one, green and blue and yellow. Is the yellow visible enough? I don't know.
Yep, I can handle it.
Okay. And say it again, 6, 3, 3. So in other words, I just put a 6 there and then I leave the others blank. And so here we've got like squares. Very bad picture. This is a horrible picture. I got to get used to this thing. And, you know, these are allegedly Voronoi cells of Gaussian integers. So these are like Gaussian integers that I'm putting in the middle here. I'm hoping I'm doing this right. Do those look like badly drawn Voronoi cells of Gaussian integers?
Yep, they look fine.
And so for the Eisenstein integers, it's sort of triangle stuff.
Mm-hmm.
And then
It's pronounced Einstein.
and then the Voronoi cells should look something like that. Et cetera, et cetera, et cetera.
Yep.
Okay, and what does the corresponding picture look like for the ordinary integers?
Looks like the red dots in a lot on a line. They're the
Okay,
centers of the
yes,
ornament
yes,
cell.
right, the red dots are on a line. So red dot, well, okay, red. And then black things between them. Something like that.
Yeah.
Not sure what kind of connecting thing I should have, but yeah. Okay, so okay, and this we think now, right? So you know I mean, I'm not claiming that these Coxeter groups exactly are the groups the same as these other group names that I'm going to write down, but the Coxeter groups are probably embedded in these. So like, well, I think the Coxeter group at top, that probably is PGL 2, comma, the ordinary integers, I think. And where's my eraser? Where's an eraser? Oh, right there. Okay. Damn, what's it doing? I must be hitting a button. Okay, okay. Yeah, I'll have to get used to this. This must be a you know, I don't have it in the good left-handed arrangement. So let's see, how do I get this to work? I'm just trying to erase that. Okay. And then meanwhile, we have this here. Okay. I need a lot of learning and getting used to how to use this.
Yeah.
So back to ordinary pencil. Okay. black. So this would be PGL2, comma, Z adjoin I, perhaps we call it.
Yeah.
And you think that the Coxeter group is actually what order, what index inside this projective general linear group? Or is your guess slightly different than that?
I had been making some mistakes at certain points, but if I had to guess an order,
Yeah,
it would be either 1 or 2. That is, I think it's either the whole thing.
I'm guessing it's going to be, I'm guessing it's going to be index 2.
I meant index, yeah.
And then the PSL will be index. Sorry, the rotations will be, what am I trying to say? Maybe I don't know. There's all these, little factors of 2 that are annoying me. I was gonna, let's see, PSL.
I think that's index 2 in the PGL in these
Right.
cases.
And the rotation group is index 2 in the reflection group. So I don't know. I'm not sure what we can conclude from that. But so maybe this is Z adjoin Z adjoin 1 to the 1/6. Is that right?
Yeah.
Okay. And yeah, so one of the questions is, these dots are supposed to correspond to generating involutions in these groups, although when I say generating, they're just generating the Coxeter group. They're not generating the whole projective general linear group if the Coxeter group is non-trivial index in the projective general linear group. So can we write these down as explicit matrices? So let me think about the top row first, okay? Can I think out loud about the top row a little bit?
Yeah.
So actually, I'm sort of thinking out loud about all 3 rows at the moment. And I may have said this before, but I'm trying to make it more precise now, that let's see, maybe I'm claiming that all of the dots, except for the rightmost dot in each of these 3 diagrams, is strictly upper triangular with 1s on the main diagonal. Is that what I'm claiming? So like, does that seem plausible?
They got a square to 1.
They have to square to 1. You don't think that's possible? Okay, then what am I trying to say? Okay. So yeah, okay. So right, I did make a slight mistake there. Right, I think I'm claiming that if you multiply these 2 together, they give you 1s on the main diagonal and upper triangular. And then let's see. I mean, what am I trying to say? What am I trying to say? That
well, I think so PSL to Z. People love this generator that's well in this matrix form. It would be like upper triangular with 1s on the diagonal and a 1 in the corner. In the upper right.
Yeah.
So that's somehow supposed to be related to like the product of the green and the blue dot.
Exactly. Right. What I was trying to say is that if you omit the red dot at the right, then the rest of the thing is supposed to be basically the semi-direct product, that includes all of the translations of the translations of the additive group of this number ring. But plus this one extra thing, which is multiplication by -1. Is that right?
Yes, so.
So, oh, okay, just multiplication by -1. Okay, so maybe, let me think. I mean, if the only extra thing is multiplication by -1, what if we allow on the main diagonal either okay, let me think. Oh, okay. So first of all, I'm screwed up, right? Okay, so we're right. We're working in the projective general linear group. Okay. So I'm right. I think that these translations are just the ones that I said. Right. So there's a semi-direct product with just two. It's made up of just these two cosets. It's got this. Right. It's one coset is the translations, and the other coset is the reflections of the number ring. And the translations should be the ones. I mean, I hope I'm not screwing up too badly, but I hope you can figure out how to fix everything I said. The translations, I think, are the ones with ones on the main diagonal and one other entry.
Sounds right. Yep.
But what are the reflections? What do those look like?
So those are what? Reflection followed by a translation? Is that what you mean?
I
mean, every element's either a translation, well, of this little group. It's either a translation or a translation followed by or preceded by a reflection.
Are those all conjugates of each other? What am I trying to say?
What do you mean? No. Huh? Were you?
But there's just a few conjugacy classes. Let's see.
In PGL2? Wait, in what?
So in the translations, those are like all there's lots of conjugacy classes there, but among the reflections.
Oh, really? Oh.
Well, am I screwed up here? I mean, like, take the infinite dihedral group. Am I saying this right?
Yeah, you're right. Okay. So you can reflect, if you've got a line of dots, like that line of dots at upper right.
Yeah.
Then we can reflect it around any, I don't want to worry about whether the red dots or the black dots, but we can reflect it around any dot. And all those, yeah, you're right, all those reflections are conjugate because they're conjugate by a translation.
So I think I fell into some stupid trap here. I kept on thinking that, we have these translations, and then we have this one extra generator, which is basically just -1. And the trap I fell into was to think that as a 2x2 matrix, that's just -1. But that's silly.
Right. It's like I mean, in the usual, yeah, you're right. It's just, if you use like the usual fractional linear transformation way of describing things, it would have like a -1 and a 1 down the diagonal.
Okay. Okay, okay.
And it doesn't matter in those two.
Right.
It could be -1, 1 or 1, -1. Those are the same in the PGL.
Right, 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 right.
I always get confused by this. Yeah, how do we extract the Coxeter generators from the sort of, how we relate those to the more famous generators of PSL2Z?
Yes, yes.
That's what
Yeah, I'm sure I've done this a lot of times before, but I'm just not, let's see. So, I mean, it sounds like, let's see, so maybe one of them is just, let's see, could it be, let's see, one of them is, you know, like 1 and -1. And then maybe one of them is 1 and -1 and 1 or something like that.
That sounds like a good guess. Yeah, if we multiply well, your conventions for matrix multiplication are different from mine, but if I multiply the first one of those by the second one of those,
yeah,
then we get a matrix with 3 1s in it. I mean, you can do it in some order, and you can get so you can get the guy 1 1 1 and a 0 in the lower left, and that's good, because that's the translation generator, and that has infinite order. So that's what the infinity is saying. So this looks good to me. So, I mean, I don't know if it's matching all standard conventions, but it is giving generators for the little Coxeter group that just includes the first 2 dots.
right. And do we have any guess for the dot at the right, the one that takes us, you know, the one that rotates an infinity gon into its neighboring infinity gon? I said rotates. I mean, that's the wrong word. Reflects. We somehow want to reflect. So what is it?
I know it's got to have something non-zero in the lower left, because we got to get out of there.
Let me just draw a bit of a picture to remind myself of what this is supposed to look like. So what, like maybe I'll just draw with straight triangles or something like that. That is a really bad picture, but and now that it's a bad picture, this is the wrong picture. Is that right? I'm supposed to be drawing the Poincare dual picture.
Yep.
So what does that look like? That looks like, sorry, that was the wrong color. It was supposed to be red. Okay. What's going on here? Sorry, I'm getting the wrong colors. Am I doing this right? Sorry. I'm obviously not used to this yet. Why
It's pretty counterintuitive.
Yeah, but something's really not making sense here. I'll give up in a moment, but let's see. Color. Damn.
That's pretty weird. I sympathize with you.
I've got that. And it's saying red. So I click on red, and then it doesn't do red. Let's see. All right, okay. Yeah, now I'm really confused. Now I'm really confused.
You want to go to home to see useful stuff.
Okay, that helps. That helps. So what am I trying to do here? All right, so I'm just stuck with black and white for a moment. So I'm going to draw Poincare dual stuff. And so what does that mean? That means that there are like infinity gons here. Let's see. Yeah, it's a very bad picture, but you can see a couple of 3 infinity gons here meeting at the corner. And there's actually a whole bunch of other infinity gons, like there's one down here, which you can barely see, et cetera, et cetera, et cetera. And so how is that supposed to help me understand this? Just to remind myself what the picture looks like. Oh, okay. So we're supposed to.
I mean, the product of the second 2 dots in your diagram should give you that third turn that's sort of staring us in the face.
Let me ask you, in a moment, let me ask you to repeat that. But first, am I right in thinking that what I want is this reflection here, reflection across, this is the mirror that I want to reflect across? Let's see. Okay, so no, maybe I got it backwards again, because there's the question of does the dot correspond to changing the thing? No, but maybe that's right. Yeah, the dot does correspond to, we want the dot that corresponds to change. Yes.
Yeah.
That's right. That's right. So okay, now did you tell me something about what that one should be?
No, I told you.
What did you tell me?
I told you a property, which is that if you go up top, the product of the blue and the red should have order 3.
Right.
And it should be this rotation in the picture, in the hyperbolic plane picture. But I think it's something like the blue dot, but with a 1 in the lower left now instead of the upper right. So maybe I
was going to have it be something like this or something like that. Does that make any sense?
Oh, well, okay. Wow. Okay. Maybe. Yeah, I hadn't thought about that. Okay. That's a decent candidate.
In particular, I was hoping that maybe I could almost see that really would give something order 3, or do I need another sign in there? Let's see. I'm not sure. So anyway, right, this is supposed to be the completely trivial one that we're supposed to use in trying to understand these non-trivial ones that we're learning about. But we can't even get the trivial ones straight.
Right.
But let's try to think. Let's pretend that we finished the easy one and go on to think about the hard ones a little bit. Okay. So to what extent is the pattern still the same? Can you tell me anything, like about the Gaussian integers 1? So all 3 of these, everything except for the red on the right should be strictly upper triangular. And
how do you know it should be? Those should all be strictly upper triangular. You just
because it seems like a reasonable guess. Because what am I trying to say? No, I should be able to say something better than that. It really should be right. But let me also write down this last one, the red one, which is not going to be strictly upper triangular. And sorry, just a really stupid guess. I wonder if we could get this to work out in such a way that which matrix the red one is exactly the same for all three of them.
Yeah, I would love it if that would be cool. I'd also love it if so like of your three examples here, the first group is included into the second two. And it'd be nice if that
Yes.
were pretty visible somehow.
Yes, well, I mean, one way it is supposed to be visible is that when you stare at these three-dimensional hyperbolic tilings, you can sort of just, you know, take a little cross section of these bubbles and you'll get a little infinity gone or something like that,
Yeah.
right? But you want something better than that, or you meant something better than that. I don't know.
I was just hoping that like
yeah.
the generators of the first of
Oh,
PGL UZ would get like mapped. There obviously is some difficulties with this, but I hope, you know,
yes,
hopefully
but,
they would be just a subset of the generators of the other ones. But
right. I mean, but you know, my plan, which of course isn't exactly working out, my plan was like, you know, looking at the second row, the Gaussian integers row. My plan was that all you have to do is just glance to the Voronoi picture at the right, and that should tell us what those three matrices are on the left. The three leftmost matrices are that, right? You just think about what are the obvious reflection operations on a Voronoi tile, right? So what are they? So don't tell me. So one of them is, boy, what are they? So they're like 45-degree rotations. Is that right? 45. What am I trying to say? They're like reflections across a 45-degree angle mirror. Is that right?
what does that mean? If you have one mirror, it doesn't make sense to say it's a 40. But they're the reflections around.
I'm staring at my picture here. I'm staring at my Voronoi picture.
Oh, okay.
See the little thing over here?
Yeah.
My cursor. And I'm saying in that picture, it's just a familiar picture, and we have, you know, the usual sense of what the 45-degree angles are.
Okay. Okay.
And so there are, you know, one's going from northwest to southeast, one's going from northeast to southwest, and but wait a minute, those but those okay, no, it must be that one of them, right? Okay, I guess you're right that they have a 45-degree angle to each other, which means that one of them, right, one of them must be a sort of diagonal mirror, and then other one of them must be a horizontal or vertical mirror.
Yeah. Right. So that gives you the, whatever you call it, the Euclidean part of the hyperbolic group. There's like a Euclidean part, there's like an affine part. There's a Euclidean Dinkin diagram, an affine Dinkin diagram, and a hyperbolic one.
That's right. That's right.
And
that's
so
right.
Right now you're talking about the Euclidean part, and that has to do with like the first two dots in your diagram, I guess.
That's right. That's right. So right. So in other words, that's all fixing one Voronoi cell. When you fix one Voronoi cell, basically what you can do is, you know, reflect it in these two different ways, and that generates a whole little dihedral group. Yes. So right. So if we were any good at this, we could pretty easily write down these first two things. And yes, and then the third one would be the one that, you know, reflects you into the neighboring Voronoi cell. And so then the fourth one, yeah.
Okay.
Well, the fourth one is, you know, the one that moves you into the neighboring bubble. You know, these bubbles that have boundaries that look like the Voronoi tiling of the Gaussian integers. These, you know, three-dimensional bubbles. Did I interrupt you? Did you finish what you were saying?
I was thinking it would be nice if the blue dot,
Yes,
if the matrix for the blue dot
yes.
contained I in the Gaussian case and contained the sixth root of unity in the second, in the Eisenstein case, because you'll notice that all the fourishness and sixishness and three-ishness is involving edges that touch that. Well, the variability involves the edges that touch the blue dot.
Yes.
Among those Gaussian and Eisenstein.
Yes, I mean, one of the things you're pointing out is that I'm not using all of the good color coding that I could in principle, right? When you color code the dots in the Coxeter diagram, you're then supposed to use the same color coding in the drawing of the tilings, and I didn't do that I just didn't do that. So that's screwed up. Yeah, okay. So in principle, we could do this, and it would.
Yeah.
Does that seem right that the red one will be sort of independent of
the number ring?
Yeah. Does that seem right?
It feels right. Yeah, I don't have quite a logical argument, but I really like that idea because it's
all right. I'll just put
it's always connected to a edge with a 3 in it.
So I'll put one question mark there, and then I'll put 2 question marks here. Because right, I'm still not sure there's not like a negative sign that should be in this first one, where I wrote the single question mark. But the 2 question marks is for the possibility that we're just copying that from the top row.
I have some stupid theory that like all these generator matrices should have a -1 because they're like reflections. But I don't know if this makes sense, but because we're doing something funny with them. But you'll notice that the way you guessed the first line, all those 3 matrices have determinant -1. So they're all not in PSL. And that sounds good to me because it's supposed to be like products of pairs of them, products of even numbers of them.
Oh, so you think I might actually have gotten it right? I mean, that's good propaganda. What you're saying sounds like good propaganda for thinking that I actually guessed right, or for the red dot at least.
Yeah. Oh, and another even better reason is like if you stuck a single -1. Wait a minute. Never mind. If you stuck never mind. Yeah. So that's my only reason for believing that. Well, apart from wanting that red stuff to be sort of the same in every case. Well, that doesn't say what it should be, but anyway, but I think it should, I think that looks good to me.
Okay, so now let me ask a silly question here. Let's consider PGL, for example, 2 comma Z adjoin 1 to the power of 1 something else. What should we try, for example?
5th.
Well, maybe that's sort of the wrong thing to say, but I want 1/5.
Oh, but you mean the algebraic integers anyway, yeah. So that's not, yeah.
Right, okay, so that was the wrong thing to say, but I should have, instead I should have said something like, what should I have said? Something like the square, no, let's see. All right, so let's see. I'm trying, I'm trying to use vaguely remembered patterns about how, things behave, primes behave a little bit similarly if they're equal mod 4 or something like that. So let's see, if we have like 3, then 7 should behave the same way. So I think it's something like, what? It's like square root of -7 and then you average it with 1, something like that, and that's how you get the generating. I think that might be the generator of the Kleinian integers. Did I write that sort of correct? I mean, that's supposed to be the generator of the Kleinian integers. Right now, I mean, I'm just imitating what we do for the prime 3.
Okay, sounds good to me. Yeah.
So we think that this can't give a Coxeter tiling in the same way that these other ones do.
It could give you.
But it seems like it's going to give us something. What is it going to give us? Go ahead. Yeah. Sorry. Go ahead. Go ahead.
I mean, you can write down things that look like Coxeter diagrams that have numbers on the edges that make them not be Coxeter diagrams in the official sense. So like, I'm confused, but I mean, you could like stick a 7 in there. You could draw diagrams like what you've been drawing with weird numbers in them that would.
Well, but those still qualify as Coxeter diagrams. I mean, you can use any numbers you
well,
want.
okay. Well, okay. I guess it depends what you call a Coxeter diagram. But yeah, they're not. They could be like infinite reflection groups, not finite. Well, these are already not finite, but.
Right. We're already in the realm of, the pretty general.
Yeah. But what I meant was something
I thought
like,
you were hinting at like fractional things or something like that, which maybe I've seen somebody do something like that. But, well, I'm sorry, go ahead.
Well, like there's this Coxeter diagram for the icosahedron or dodecahedron, which is like, there's a 5 and a 3 in it.
Yes.
And
right. Those are.
And if you replace that 5 with a 7 or something, you'd get something exotic. Anyway, I don't know if those are at all are relevant. I was imagining. I don't know if I liked it, but I was imagining like groups that have like dense orbits acting on the space or the. I don't know.
I mean, I suspect that what you're hinting at really is related in some very peculiar way to this Kleinian integers. But I was actually thinking that, we really have to change the concept from a Coxeter group or Coxeter tiling to something more general. Because again, I think we've drawn, right, let me see if I can remember vaguely what the Coxeter tiling looks like. Damn, I'm still having this damn color problem here. What is it telling me? Click here and then select it. Okay, no.
Well, did you do that? Did you first click there and then select the color from the color palette?
Let's see, color 1. Click here.
Try following the instructions. So something did happen there. Okay.
All right. So what am I trying to do? I'm trying to draw vaguely what the Kleinian integers look like. So looking at my formula, it looks like I've got, again, what was the square root of 7? It was about 2 point something. No, 1 point something. Is that right? No, 2 point something.
No, you're really out of it. Yeah, it's more than 2. 2 point. I forget what we said.
Let's see.
Does it really matter?
I
remember I guessed.
It helps me a little bit, in drawing the picture. I mean, we might get hexagons or we might get parallelograms or something like that.
I remember I guessed and then like typed it in and was annoyed at how bad my guess was. I'm gonna do 2.64. Okay, you there.
2.64. Okay,
I would
so
have guessed 2.6 this time, so I'm getting better.
okay, so that's like 1, and then this is, I don't know, that's supposed to be 2.64 or something like that.
Okay, looks good to me.
But then I think it's going like, I think I'm saying it's like this. You know, I mean, maybe I got this totally wrong, but this is what I think the Klein integers would look like. These, and then what would, okay, and then what would be the Voronoi thing? So it would be like,
Yes.
sorry, what is it?
You got to put a dot. You can at least put a black dot right in the middle of those triangles. I mean, you know it's going to happen there, right? Am I that confused?
Oh, what do you mean middle of the triangle? I thought you meant
Well,
that
some kind of
I'm going to have
center.
something like this or something like that.
Okay,
you know,
well,
I'm trying
cool.
to,
yeah, that's fine.
draw
Yeah.
the things.
Yeah. Yeah.
So they're sort of skinny hexagons, we're saying, or something like that.
Yeah, I guess.
Very badly drawn, but oh, really, these are really badly drawn, but something like that. So they look hexagons, but bad hexagons. And what does that mean? Yeah, well, so I mean, these hexagons are just not as symmetrical as the hexagons for the Eisenstein thing. So what does that mean? Is it plausible? You know, are we going to get a tiling? The tiling going to have some symmetry, but the symmetry is not a Coxeter-like symmetry.
It's a good puzzle because from the description of the group, PGL2, comma,
yes,
blah de blah.
Yes.
It doesn't sound like that. Well, this is a stupid thing to say, but it doesn't initially sound like that group's going to be dramatically different depending on which prime you take. I don't know what that means. I guess it's false. But then, so you should get some group, okay, and it'll have some generators, but for some reason it's not a Coxeter group. So so it should have some presentation that's sort of nice, and ideally, if like a presentation that makes it look sort of like the other ones, like the Coxeter ones. You may need a new kind of presentation to make them look similar. And are you saying that, let's see, are you saying that like some subgroup of this thing should actually act as symmetries of this lattice of red dots? Some subgroup of this PGL2 Kleinians?
I mean, the whole group should. Right? Isn't that what I'm claiming? Well, I mean, I could be screwed up. I could be saying something false.
Well, but PGL2Z, okay, it acts on the PGL2Z acts on the line, on the projective line for Z. So, so it almost acts on the. It doesn't act on the integers.
You think it might be acting in some out of focus way that's not going to preserve these?
I mean, PGL2Z doesn't act on Z, right? So it maps integers to rational numbers and stuff like that. But a part of it does. Part of it is portion of it is just these. The Euclidean portion of it is just these reflections and translations.
Yes.
So for this example here, we could hope that like some portion of this group will be actually acting on the lattice of red dots that you just drew.
Well, yes. And aren't I claiming that it'll again be these upper triangular things?
That sounds
You know,
reasonable. Yes, those are, I mean, using my what do you call it, fractional linear transformation intuition, those upper triangular ones will indeed be, they'll just be acting as linear transformations with coefficients in the number field. So they will indeed preserve those red dots.
Yeah. So let me go back for a moment to something you said about,
I think.
You know, you were talking about the Gaussian case and the Eisenstein case, and you were hoping that there was like a nice uniform pattern that, what was it? The second matrix would look like, I forget whether it was the second or the third matrix, but it would look like something like
The blue one, the second one should have like
one, yeah.
the number, should have the number
right.
rings really visibly in it. It should be like wearing it on its sleeve somehow.
That's right. That's right. That's right. So the 1 to the 1/4 for the Gaussians and 1 to the 1/6 for the Eisensteins, but I don't think we mentioned anything about. Am I saying this right? What am I trying to say? I'm trying to think about, maybe I'm wrong, but I was thinking maybe there was some conceptual role played here by the units in the number ring. So, you know, right, there's these 4 cardinal units in the Gaussian integers, and then these 6 units in the Eisenstein integers. And I'm trying to figure out, I mean, as elements of PGL2, they get washed out because they're invertible. So what am I trying to say? I don't know.
What are the units in the last example?
I think none of them have any units except for the Eisenstein and Gauss.
So just 1 and -1.
That's what I think. I mean, maybe I was hoping to explain the pattern of the index. You know, the pattern of the Coxeter group being a certain index in the projective general linear group, and somehow relate that to the units. But that doesn't seem to be working either. So I don't know. I was trying to make some stupid guess, and it didn't really work. So maybe I'm about ready to hand over the.
Yeah, this sounds like a really good thing to work on, and sort of embarrassing to work on.
Sure.
When anyone's watching, because I think the only way I know how to do it is to like make tons of guesses and try them. And
well, you also proposed the method, or you actually started almost carrying out the method of challenging people on Twitter or something like that.
That's another way that's also less embarrassing. Depending on.
I'm not sure it's less embarrassing, but yes, go ahead. Embarrassing for who?
Well, yeah.
Let's see. Yeah. So let's see. Is there anything else I should say before we change topic here?
Yeah, I was just saying that, like,
there's lots more stuff to figure out here.
I'm eager to change the topic, but not because it's a boring topic.
Sure.
Just because I think we can figure some stuff
Sure.
out. Yeah. Now you got me really curious to know, like, what are these sort of post Coxeter groups that aren't Coxeter?
Yeah, I mean, right. I mean, saying, you know, you just stare at those Voronoi tiles and they have some symmetry, but they're not full symmetry. So it just seems like there's something going on, some kind of tilings that are, you know, have some symmetry, but they're just not as symmetric as Coxeter tilings. I don't know. That's all I have to say for the moment about it. So, okay. So
I have one other silly thing to say.
Go ahead.
As if these weren't already hard enough.
Yes.
There are, I believe you can like copy this stuff with quaternions, with, I guess they call them orders or in the quaternions,
Right, you did hint at
subrings.
that earlier. Go ahead, yes,
Yeah.
go ahead.
Yeah, so you could, so there are, again, like some nice supply of subrings of the quaternions that you could do PGL2, that subring. And then I think those should be, so those should be acting on a 5-dimensional hyperbolic space.
Five-dimensional.
So the
five real dimensional hyperbolic space.
Yeah. I just remember this because I know that like the reals, complexes, quaternions, and octonions, if you look at PSL of those things in some funny sense, you get the Lorentz groups for dimensions 3, 4, 6, and 10. But then if you subtract one from 3, 4, 6, and 10, you get the dimensions of the hyperbolic spaces. So that would be like 2, 3, 5, and 9. And so we're doing the 2 and the 3 case here. 2 and 3-dimensional hyperbolic.
All right, that's very interesting. Very
and so there should be a little bit of fun left in the 5 case, and then maybe even in the 9 case, but that would be like really, really weird.
Octonionic weirdness, is that what you're hinting
at? Yeah, because you have to like do backflips to even know what you mean by the group PSL.
Sure. Okay. But 5-dimensional.
But 5 dimensions, yeah, it should be neat. And there's stuff that is known about like quaternions and hyperbolic Coxeter groups. So
yeah.
So anyway, that's just like in the interest of like, if we ever get anything to work, how we can like squeeze more the last bit of toothpaste out of the tube.
Sure. Right. But I also feel like I'm getting a little bit of insight to, I don't know, when I hear people talk about Kleinian groups and stuff like that. Well, I mean, again, there's the joke about how Kleinian groups don't have that much to do with Klein, but they really do have something to do with Klein. And you know, I feel like we really are relearning some of the history of what Klein was really doing and other people were really doing. And I mean, there's other directions of generalization here. I forget what I was going to say. Okay, so I think I'm ready for the change of topic.
Okie doke.
Okay.
I think I'll share this. I'll take over the.
Okay, so I just have to stop share or something like that.
I can override you. I can just grab it. Yeah.
Okay.
Since I'm the host.
Okay.
So I've been thinking about, well, it started out for me thinking about the Rosati involution.
Yes, okay.
But then it turned into me thinking about all the prerequisites of understanding the Rosati involution.
Sorry, you just reminded me of what I was going to say. I was just, but it's actually perfectly helpful because I'm just trying to point out that there really is a good segue between these two topics. You know, I'm just trying to remind myself that it's not like these are really different topics. This really is, you know, all that stuff we were doing really did have to do with neuron severity. Neuron severity.
Yeah. So these should be the really nice, some of the nice juicy examples of figuring out neuron severity.
That's right. So I'm just trying to remind myself or anybody else that this is actually secretly the same topic. Okay, go ahead.
Okay, so I'm going to be talking about, so X is an abelian variety.
Okay, I think I'm going to take paper notes on this. Go ahead. Yeah.
And then I'll be thinking of X as like V, a vector space over L, a lattice. So V is like a complex vector space. L. I need some names for things. Well,
Sure.
I don't need them, but
Sure, this is all very good. Okay.
so then
Anybody know the date? Is it the 13th or something?
it's the 14th.
14th.
Pi Day. Yeah.
Pi Day. I didn't know that. Okay.
Exactly.
Yeah.
Okay, go ahead.
Yeah. And actually, now that I think about it, it turns out when I was like stuff, it turned out that like everything, well, for a long time anyway, everything works for a complex torus. By which I mean, I guess that might
Right.
mean different things to different people, but what I mean is this thing here.
Right. Yes,
So-
it does mean different things to different people, but yes, but I know which one you're talking about at the moment.
Yeah. So it's a complex manifold, complex compact Lie group.
I mean, it sounds like you're saying instead of ruling these out up front, you can just leave them in and let them explode when
Right.
something
Yeah.
goes
You
wrong.
can just exactly. You can just see
How
what
far
they
it can
do.
get
Yeah.
before that.
So, well, okay. I don't know. Let's see. I'm trying to debate how to ruthlessly efficient to be. I think it won't be completely ruthlessly efficient. So there's this thing called the Picard group of X. So that's like the
Yes.
group of all the isomorphism classes of holomorphic line bundles on X. So there might be very few if X is not if X is not an algebraic variety, I guess. So those are like the cases that like you
The mere complex toruses.
yeah. So this could be very small. But it's a topological group. It's a Lie group. It actually turns out to be like a complex Lie group, a complex, a group object in complex manifolds. But so it has an identity component. People often call it like peak 0x. So this is like the identity component, but I guess it has tons of other names. Well, not tons, but too many. So it's like called the Picard variety sometimes.
Right.
Maybe a better name for it I don't know if it's better. A different name for it is like it's the Jacobian of X.
Jacobian.
So it's like the thing of line bundles that are all holomorphic line bundles that are trivial as topological line bundles.
Yeah, I'm just being silly. I can't remember when people use the terminology Jacobian. I'm so used to using Jacobian for curves. I always get confused between curves and being varieties, but it doesn't matter. I'm just
you can define a Jacobian for any variety, I guess. It's the
okay.
It's the thing of holomorphic line bundles that are topologically trivial, or you can just define it like I did. It's like the identity component of the Picard group. So that's like sitting inside there. And then there's this, so you can do a little short exact sequence. So you can do this quotient group. And this quotient group is one of the various ways to say what the Néron-Savary group is. So
yes, okay, good.
So we were like, yeah, so we were like wondering some stuff about like, oh, why were we like thinking about these so much and not thinking about this
right
so much at the same time?
Right.
I believe that this sequence splits, by the way, which is, I think, sort of why we were able to get away with that. But I have to make sure that that's true. But I think there's like a way to pick.
I think that's what we ran into. Yeah, that's the way it seemed, that it really did split. And that the splitting, giving the splitting was just equivalent to picking a base point or something, or having it actually be a group rather than an affine group. But don't trust me on that. Something like that.
Yeah.
The splitting was very moderate extra structure.
Yeah, so I guess I'm mainly going to talk about, well, I'll talk a bit about both. So I'll talk a bit about both the Néron-Severi and this Jacobian.
Okay, yes.
So both of them, well, okay. So part of what was like confusing me for a while is that this Néron-Severi group has like a bunch of different descriptions.
Yes.
And there were like 3 that were like really seemed very prominent.
Right.
Well, that is 3 ones in addition to the one that I just gave.
Right.
So the first one, which is one that we've talked about, is it's like the group of. So well, here I guess I'll make it even more. So one of it's like it's the subgroup of the second cohomology of X. So the second cohomology group is classifying topological complex line bundles on X.
Yes.
But only some of them can be given a holomorphic structure.
Yes.
So, well, this is still like a somewhat abstract description. Well, compared to the ones that will follow. But as so some of this is, I'm just telling you stuff that you've said, but
sure, but it's always helpful.
Yeah, no, I sometimes, like, if someone tells you something you said, then you actually think, wow, okay, it was actually right.
Right.
So, so as you noted, you can think of these cohomology classes as having these nice cocycle descriptions, which are anti-symmetric 2 cocycles. And so we can say it like that, and then I can put in the extra information that's this extra clause here. So we can say it's the group of so I guess alternating. I guess that just means the same as anti-symmetric here, but alternating
I hope so.
bilinear maps. I'll call it A for alternating from the lattice times the lattice to the integers. That looks too much like a plus sign.
It really did, but I thought you were trying to say that.
Yeah, no, I just can't draw very well.
Okay.
So that, well, if I just stop there, that would be a nice way to describe H2 of X with coefficients in the integers, but then we on this clause here. So such that, for some reason, although you said this, it didn't soak in to me until I really thought about it more.
Right.
So there's this condition such that, well, okay. So these things here.
Sloppily. Go ahead. Yes.
Yeah. So these things here, they always extend to things, which I still will call A, I guess. So the lattice is sitting inside the vector space. And then the lattice is sitting inside the vector space. And so then these extend to real bilinear anti-symmetric guys. I'll still call it A. So then it makes sense to write down this equation that A of IV IW is A of VW. because you don't know that V and W are in the lattice.
Right.
So we need to extend it that way. Okay, so that's the one thing, and that in some sense should be a certain pretty computable way of describing the Néron severity group if you like take the time to understand which of these, what these maps are like and which ones have this property.
Yeah, I mean, it is homework for me to try to figure out, when I did give something, when, what did my equivalent of what you just wrote down, what did my equivalent of it look like? Because it didn't look exactly like this, but yeah, I think it was equivalent. So that's homework for me. Go ahead.
Yeah, so then there's this other description that people love where your goal is to think of this A here as the imaginary part of a sesquilinear thing.
Yes.
And so then the little fact one uses is that whenever one has a bilinear, whenever one has an anti-symmetric, whenever one has an anti-symmetric bilinear form like this, which has this property, then it's the imaginary part of a unique sesquilinear map from V times V to C.
Yes.
So, and that's just like some fiddling around with algebra to define it and to get back. So we can say this other description, which people seem to love. Well, you love it, and everyone loves it. Sesquilinear maps. I'll call it H for Hermitian,
Right.
from V times V to C. Well, now I need to remember that we wanted it to be that on the lattice points. Oh, sorry. Such that if you take the imaginary part, so that's getting us back our A, then the imaginary part takes lattice points to integers. Okay. So the idea is just that M of H is what we were calling A.
Right, that it really came from this integer valued thing by tensoring with the reals. Well, actually, tensoring with the reals, yeah, it gives you the anti-symmetric thing.
Yeah. So there's all this funny thing about like reals versus complexes coming in here. So here this is basically here we're tensoring with the reals, and then the complex numbers sneak in here just as this property, but then there's this fact that like a real linear maps to R from a vector space correspond to complex linear maps to C. There are these games being played here that for some reason are not quite as familiar to me as they should be about like fiddling. They will continue.
Yeah. It's not just the familiarity. There are some things going on here that it's sort of seem mechanical, and I don't have the good concepts. I don't have the really good conceptual story about them yet. Can you go back to the previous screen just for a second? So, sorry, I'm not technically competent to gesture at the screen, but I'm looking at that thing that we both commented on before. Yeah, that thing right there. And so I guess sometimes when I try to say that, I say something like, that A is invariant under the one parameter group generated by the complex structure. And that's probably the way I usually say it. So, when I first looked at what you wrote, it just, it said, my formula blindness made it hard to see what was going on. But
Yeah, that's
Right.
equivalent to,
Yeah,
it's invariant under this circle group action.
yeah, there's also some trick going on there. Isn't there a trick going on where you can also just say that because it's invariant under this 4-point circle group, and because it's quadratic, that means somehow, I think, that it's actually invariant under the whole continuous circle group. I don't know. I'm not sure if that's true, but sorry.
I mean,
Okay, yeah, go ahead.
I mean, it is true that this is just saying invariance under, it's obviously saying invariance under that 4-point circle group. And then we can leverage that out to get invariance under the whole circle group. Yeah.
Yeah, something like
I mean,
that.
I
Again,
have some,
I need to think about that more, but
I have some
that's good.
more calculational than geometric way of seeing why
Sure.
that works. Basically, you'd like, but yeah, so.
Okay, so I'm slowing you down a little bit here because I wanted to go back to that screen, but you can go ahead back to where you were or whatever. Go ahead.
Yeah, no, it's fine.
Okay. And just let me know if I'm slowing you down too much.
Right.
Go ahead.
Yeah. No, so no, I do want to, like, in some sense, like, get some of this is like reviewing stuff, but I'm just trying to, like, get it really nailed down in my mind.
Sure.
So okay, so then there's this fourth one, which they really like for deeper work, and that one, like, was freaking me out because it seems pretty different at first. So fourth description is that it consists of maps of tori. Let's see, real tori or complex tori? Phew, boy.
Maybe I haven't heard of this one, but go ahead.
Let's see. Boy, I thought sorry.
Sure, that's fine.
Yeah. Wow, this is. I think I mean.
Sorry, were you screaming about technical things or about just annoyance at your own thinking?
It's the math that's bugging me. Yeah.
Oh, okay.
So maps of complex tori from our complex torus X to this thing, which I will need to discuss, called the dual torus, X dual.
Yes, good. Okay.
So of course this one looks sort of different than all the previous ones. And
I'm not sure it does, but go ahead.
Okay, well, I mean, at least at first it does, because the others all mentioned vector spaces and this doesn't. But yeah, there's
okay, go ahead.
But there's, well, but it is supposed to be ultimately the same, and so it winds up not looking so different after all. But part of what was is just like, what's this dual torus? X dual. Because I seem to have been getting, like, reading places that give like two really different descriptions of what it is.
Yeah.
Which I couldn't even see why they were the same thing.
Yeah.
So one of them, answer one, is that remember, you have your torus. It is really canonically a vector space mod a lattice. That's what we started with. And so then you can define this dual vector space. And we should be careful here. There's like the real, sorry, this is perhaps in the wrong order of the words, but it's the dual real vector space, the real dual vector space.
Yes.
But by the way, which is a complex vector space, which is naturally a complex vector space, because X was.
I think I might have mentioned that in the
Yeah,
last
you did
discussion.
mention. Yeah, you did mention that.
I did. I didn't explain it in any good way, but I was groping towards something like that.
Yeah, you're right. No, that's part of the sort of funniness of it all.
Yes.
But I think
again, there should be some very obvious story about how this happens. But yes.
Yeah. Well, I think I know that you can just.
Yeah, it just annoys me that I can't say it.
Well, the way to say it is that, like,
ahead,
you can. The guy in here is a linear functional from V to the real numbers. And you can pre-compose any linear functional with multiplication by I, because V is a complex vector space.
Yes.
So you could define that to be how you multiply. So then you get a new real linear functional that way by precomposition. And so you can define that to give you a complex structure on V dual. That's a way to say it. But it is funny to me just because, like, I've thought for a long time about linear algebra, and I never heard anyone trying to do that before. But it's really essential here somehow.
Yeah.
Okay, so that's that, and then there's this thing. This star is getting used in like tons of completely different ways here. So this is like the guys in the dual vector space, such that when you apply them to vectors in the lattice, you get integers. So these are like the integral linear functionals in some sense. So there's like a pairing between V and V star that gives you real numbers, and there's a pairing that restricts to a pairing between L and L star that gives you integers.
Yeah.
And then finally, so since we have those two things, we got a lattice sitting inside a vector space, we can form a torus by taking the quotient. So this dual torus is defined in this approach to be the dual vector space mod the dual lattice.
Yes.
So this is to define it.
Say that again. This is what?
This is one way to define the dual torus.
Yes.
And then, like, I'm still confused about this, but there is this other thing you can do. Leave gives you an isomorphic, naturally isomorphic torus. So let me just tell you, I don't know, let me just torture you by telling you this other way.
Okay.
So same background here, right? So our X was this complex vector space model lattice. So, but now we're going different way to get this dual torus. It's a lot faster. It's just the Pontryagin dual of this lattice here. So it's maps I'll call it like maybe like as abelian groups from the lattice to the circle. So that's going to give you something torus-ish, because the Pontryagin dual of a finitely generated free abelian group is going to be a torus.
All right, so it sounds like you're doing something very slick there, but let me just see if I heard correctly what you said. The dual abelian variety in this complex context, is the Pontryagin dual of the lattice, the period lattice.
Yeah.
Pontryagin dual of the period lattice is a slick description. Okay, that's very helpful.
So yeah, because this is like so much shorter, it seems to be useful because of that. That you just like get it really fast.
I wasn't sure if my audio glitched there, but you were just commenting on that this is because this is so slick and it's useful because it's nice.
Yeah, just because it's quick. Mm-hmm.
Okay.
I could try to give the explanation of why these are isomorphic.
That sounds like a good homework exercise for me, but you can say whatever you want about it.
Maybe I'll leave it as an exercise, or I can talk about it some other time. I feel like if I try to explain it.
I mean, it depends on how many more punchlines you want to get to today.
I want to get to,
because now you've got me worried that like I somehow screwed up the time and I didn't leave you in with enough time to talk or something. Maybe I got confused by daylight savings time or something. Sorry, go ahead.
No, you showed up a little late, but
oh, that's right.
And
yeah,
talked a little bit long.
That's right. That's right.
It's okay.
Okay.
So I won't try to explain that. What I will feebly attempt to explain is why. Is like why did I talk about this? Well, okay, I brought in this dual torus because I had this claimed description of the Neron Severi group in terms of the dual torus, involving the dual torus.
Yes.
And while I'm at it, though, before I go on to try to explain a little bit about that, there's like this another cool fact. Another reason for caring about this dual torus, which you probably know perfectly well, is that this thing that I was calling the Jacobian.
Yes.
The connected component of the Picard group that is naturally isomorphic algebraic equals to this dual torus. So you sort of know that because we like talked about how Albaneses are dual to Jacobians, and
yes,
in this case, the Albanese of the torus is just it. Oh, sorry, this is wrong. Sorry, I gotta fix this. No, this is right. Sorry, this is right.
It's probably right for the abelian varieties. It might not be quite right for complex torus.
Yeah, let me think about that a little bit. Yeah, so for every complex torus has at least one holomorphic line bundle on it, namely the trivial one.
Yeah.
But now I'm getting confused about like if there are any others.
Well, I think it varies. Like, supposing you take a complex torus by taking elliptic curve, Cartesian product, elliptic curve, Cartesian elliptic curve, but then at the very end, multiply by an abelian, by a complex torus, a complex torus that's just like not an abelian surface, but is two-dimensional.
Yeah.
So you know what I mean? That's going to have something. That's going to,
okay. Right.
It's like
you can.
It's maximal abelian, maximal algebraic, whatever, something.
Okay. Yeah, you're right. So so this is like if X is an abelian variety, then it's just then this. But in general, it can be smaller, right? You're right. Yeah.
Smaller or co-smaller, I get confused. But yes, something like that.
Yeah. Yeah, good point. Yep. So this dual torus it's sort of cool. It shows up in both these, describing both of these parts. I like to think of this, yeah, I'm sure you do too, as this is like the discrete part of the classification of the holomorphic bundles, and this is like the continuous part.
But sorry, can you say what again? What's the thing that's showing up on both sides? The thing that's
This
showing up on
dual
both sides?
torus. Well, at least when X is a abelian variety, this is
Right.
X dual, and this is maps from X to X dual. And so that's,
Let me just try to write down quickly some version of that slogan. So say it again, the dual abelian variety is showing up in both the discrete and the continuous classification?
yeah, maybe, well, maybe it just while you're writing it down,
Sure, go ahead.
I will write it down in some other way. So this is like,
Okay. I mean, I have some vague guess that this is also related to your answer to my question last week about, what was going on about the two forms and the one forms. They're both getting complexified.
oh yeah, yeah,
I'll think about that.
that's probably right. Yep, that sounds right. Yeah. Yeah, so here's my way of saying it. Like you take this exact sequence and like both ends like to be described in terms of this dual torus. So, right, so I wanted to attempt to say a little bit about how we get this description of the Néron-Savary group in terms of the dual torus from some of our other descriptions.
Yes.
And so it seems like people, so far I would like to get it straight from description 2, which I think of as like more simple than this one. But description 2 is about this alternating bilinear map with a property.
Yes.
But anyway, it seems like people, maybe it's nice that the property has gotten sort of absorbed.
Yes.
into the sesquilinearity here. So they seem to get it from, they seem to get this last description out of this description sometimes. And so the idea is just sort of probably what you were, I just imagine you guessing it. It's like, well, if you have something that can like eat two variables, spit out a number, then it can eat one variable and then spit out.
I mean, there's some sort of joke here about eating curry. Okay.
Yeah.
Very obvious joke, but I never heard it before. Right. Okay, go ahead. Yes.
So yeah, we sort of curry this.
Yes.
Yeah. So basically, that's sort of right. But
yeah, I mean but yeah, that's very helpful because whenever I think about currying, I go back to that eating metaphor. Yes. Go ahead.
Yeah. So I always talk about eating and then spitting something out, but I don't know.
I'm not sure how that goes. I'm not sure how multicultural that works. I don't know.
Yeah, that sounds like
cross-cultural. I don't know.
Yeah. Okay. So So, okay, so let's start with our H, which is sesquilinear. And it has this integrality property. So this is one description of a guy in the neuron severity group. So, well, of course, with sesquilinear things, you have to, well, if you're trying to be careful, you may want to worry about which side is the linear side and which is the conjugate linear side. So, and that's what was like freaking me out the most about all this stuff, is because, like, right, this map between abelian varieties that we're getting, it's just, oh, there's nothing conjugate linear going on there, apparently. It's just like algebraic geometry. It's just like everything's holomorphic. So I was getting really puzzled.
Yeah, this still bugs me, but I have some vague ideas about why it's okay. But go ahead, yeah.
But yeah, so I will attempt to give a story about that. But let's. So I will. So sorry. So I will. Let's see. I guess I'll go to my usual physics training, which is this is it's like conjugate linear here.
Okay.
And linear here.
I mean, I think that just happens to match my convention.
Okay, good. Well, it is
not sure why, but yeah, go ahead.
But anyway, so it's not the one that any of these math books I'm reading use, but okay. So,
oh, that's interesting.
So okay, so what we do is we take so the big, sorry, this is the very suspenseful part here to me. So, okay, so what we'll do is we'll choose a guy, choose, sorry, choose a guy in this vector space. Let me call it V to be nicer. And form this map here. So notice this map here depends linearly on V.
Yes.
But what it is it's something conjugate linear.
Okay. Okay.
So this thing here is a map from V conjugate, the conjugate vector space, to C. It's a linear map like that.
Yes.
That's how I'll think about it. Okay, so this thing is, so it's a linear, I'm just saying it again, but I'm saying it a different way. It's a linear map. So this is like common in vector spaces from V dual, sorry, from V conjugate to C.
Yes.
But now, so here's one important trick. Oh, I shouldn't say vector because we have real and complex vector spaces running around.
Okay.
So let me just sort of, I think, I don't know if do ring theorists say something like this. This means like HOM of C modules or something like that.
I'm sure somebody says it.
Yeah, okay. So then one key trick is that there's a canonical isomorphism between these and real linear maps from V to R.
Yes.
So this is sort of almost like something that we were talking about a minute ago that you mentioned.
Yes.
So like what you had mentioned once upon a time was that real linear maps from V to R correspond to complex linear maps from V to C. V here is a complex vector space, right? So yes. That you can, so that, well, like to go from one of these, you can take its real part and get one of these, but then
Yes.
there's no way to go back.
Yes.
But that same style of argument also works to establish this isomorphism. If I have a conjugate linear map,
Yes.
from B to C, I can take its real part and I'll get a real linear map to R.
I mean, I think of this as a sort of pons asinorum trick, you know, that theorem in Euclidean geometry where you use the fact that a triangle is equivalent to its own dual or something like that. And
so who's the
who's the asinorum?
Who's the ass and who's the pun? No, who's the symmetrical thing here?
It just has something to do with the fact that the complex numbers. I mean, you're just exploiting this automorphism of the complex numbers. Is that what you're doing?
I think so.
Yeah.
I think so these are like, this is the triangle and this is like the reflected triangle or something. These are like
right. So I mean, you know, you're using a field isomorphism, which just happens to be an automorphism. But if you don't, if you just try to not get freaked out by the fact that it's actually an automorphism rather than just an isomorphism or something like that.
Yeah. Yeah. So, okay. So notice then that this map here, we can actually identify it with a complex linear map from V to C in a natural way, and so that's
yes.
Well, what can we do? We can do a bunch of things, but either of these two things was what I've been calling V dual, the dual vector space. So we can say, using these identifications, we can use an identification to say that this thing is in V dual. I mean, even though it started out as a conjugate linear map from V to C, you know, we could think of it as a linear map from V to C. So this was like freaking me out for a while.
Yes.
And then right, okay, so sorry, let me just move on here. So remember what I'm trying to do. I'm trying to turn this thing into a map from the torus to the dual. I'm trying to turn H into a map from the torus to the dual torus.
Yes.
So far what I've got is a trick where you give me a guy in the vector space V, and I get a guy in the dual vector space.
Yes.
So that's pretty good step.
Yes.
Towards getting a map from the torus to the dual torus.
Yes.
So that's what I'll do.
Okay.
Yeah. So I mean, maybe this will someday all seem very banal to me, but it's just sort of something a little slippery about it, which made me want to think about it. So
yeah, I want to understand this better, but go ahead.
Okay, so let's just recap. So our H here gives us this map sent from a vector in our vector space to this map here, which I'm just repeating myself. which to be honest is a conjugate linear map, but which can be identified with something in the dual. And so to show well, let's see. I'm gonna be very slow.
Okay,
So I won't attempt to skip any steps. So
that's fine.
okay. So then I'll call this, well, anyway. So we get this map from V to V dual. What's happening? And then, of course, we can always compose that with quotienting by this dual lattice that's sitting inside the vector space. Yes. So we can always get a map from V to the dual torus.
Yes.
But what we really want is a map from the torus to the dual torus. So we're hoping that this map from V to the dual torus actually factors.
Right.
Actually factors through here. Yeah, God, that's awful. And so to check that, we just have to check that the guys who are actually in the lattice here,
yeah,
get sent to the identity element here. So let me. That is to factors. It's some abelian group. Guess it's some other isomorphism theorem. So sorry, let me try to draw that thing a little better. So X, remember, that was the vector space modulo of the lattice. And so we're trying to get this map from V to X dual to actually factor through X mod the lattice. So we need guys in the lattice here to actually get sent to the identity here.
Yes.
But that's the integrality property of H. So H has the property that if V is in the lattice and you stick in anything else in the lattice, you get an integer.
Yes.
So if you've got a guy in the lattice here, it gets sent to a linear functional that's takes integer values on the lattice. So then when you go over here, it's the identity on the lattice.
Yes.
So you get it. You get it since H takes pairs of lattice vectors to. Sorry. Oh no.
What is it?
H does not take pairs of lattice vectors to the integers. The imaginary part of H.
Oh, yes.
Takes lattice vectors to integers.
Yes.
So this is the type of thing that like to drive me bananas.
Sure, sure.
Sure. So what I said isn't quite right.
But Phil, something's supposed to work out.
It's gonna work out. Man. So anyway, you can see why I hope you see why I spent some time thinking about this, because it's
sure.
So like I think maybe I'll quit because I get confused. Like one attempt to solve the problem would be to stick imaginary part of H in here. Place H in the imaginary part of H. That might actually work, although it would not be a homomorphism. I mean, it wouldn't be a homomorphism. It wouldn't be a sesquilinear thing anymore. It would just be like the imaginary part of it. Maybe let me attempt to weasel out. That is not to weasel out, but let me attempt to escape my trap.
Okay.
Because it might actually work. So let's see if that works. So I'll change my tune here and say, okay, I'm going to use the imaginary part of H, which is this thing we were calling A, which was the thing I wanted to be using in the first place.
Yes.
But it seems like the books I was reading didn't have that idea. My system is slowing down or something. So I'll try that. Okay, so this imaginary part of H thing, or this is just a real linear functional on our vector space. So this thing is in Hom R from V to the real numbers, But luckily in our Pons Asinorum, we saw that space is also, that's another description of the dual of the complex vector space V. So I mean,
yes.
So anyway, whether or not we need to think of it that way, I mean, we can feel like we can think of that as like a complex vector space V dual. So that's what I'm gonna do then. I'm gonna use this imh here to map to V dual. And that quotient's down to map to the torus. And it gives you integers on the lattice. So this factors through, it factors through the V mod the lattice. So here what I've done is I've like gone real, so to speak. This is a real linear map. And so if we do it this way, then we're sort of stuck with a bit of a debt because we've got a priori real algebraic or real smooth map from the torus X to the dual torus.
Yes.
But those are complex tori, and I think we really do want a map of a complex tori.
Sounds very plausible, yes.
Yeah. So anyway, so I guess there's some more work for me to see if that's true, but at least that's like just checking an extra property of this map.
Yes.
So, well, let's see. Since we're past time and I don't want to encourage us to keep going on forever too much.
Okay.
I have more things to say, but this is probably like the main thing. I mean, so what I would then go on to do if we got this straightened out is like talk more about the Rosati involution, which people.
Yes, that's what I'm sort of expecting as the punchline to this story. Where the Rosati involution is.
I can tell you one punchline. Punchline pretty quick, which is that. So there's this common way of thinking about the Rosati involution that requires choosing a principal polarization to even define it.
Yes.
But there's I think something that you can do already here, which is that if you have a map from one complex torus to another,
Yes.
then you can dualize it, and you can get a map from the dual of the second one to the dual of the first one. So this type of duality works like you might hope duals.
Yes. Yes.
And so given this map of complex tori, you can dualize it. But the funny thing is that if you dualize it, well, you get a map from X double dual to X dual. But X double dual is naturally isomorphic to X, and this works the way you'd hope.
Yes. Yes.
And so
you have an opportunity to ask whether it's
whether they're the same. That's right.
Yeah. Yeah.
And so I believe the answer is that they are, I believe, well,
or something. Yeah.
Cautious,
Go ahead.
I'll just say that, like, I believe that for it, certainly I believe that, like, for a polar, if your line bundle was a polar coming from a polarization, it would be self-dual in a sense. But I suspect that it's got to be that, like, it's true for every line bundle. But now I'm beginning to run into questions and puzzles because like, people seem to really say, I could be getting something, I could be forgetting things or getting things wrong, but like, I had said that, like, line bundle elements of the Norontsev group are just like maps from X to X dual. But now I seem to be, like, changing my tune and saying, no, they're maps from X to X dual that are self-dual in this sense. Because in the other more fancy descriptions of the Norontsev group, in terms of the Rosati involution, they say that they are endomorphisms of X that are self-dual.
Yes.
In some sense. So that's like supposed to be a trivial extra property that you're adding on there.
Yes.
So I guess now I'm confused again about, so I guess I need to check to myself or look up stuff. Is it like all maps of this kind, or just ones obeying some non-trivial property that they're self-dual? I mean, notice I was going in the one direction and having enough trouble with that. I was starting with an element of the Norontsev group described in this H way, and then I was cooking up a map from X to X dual. But now that I think about it, you know that, like, this map from X to X dual, it's sort of really coming from this map from V to V dual.
Yes.
And this map from V to V dual was coming from this bilinear form.
Yes.
But it wasn't just any old real bilinear form. It was an anti-symmetric bilinear.
Yes. Yes.
So there was an extra property of this map from V to V dual that was there.
Yes. Yes. So yes. So I'm expecting this extra property to manifest at this level of the map of complex toruses.
Yeah. So yeah, it should probably be there, but for some reason in the stuff I've been reading, they only talk about it at the stage where they've chosen a principal polarization and use that to identify X with X dual. And I'd rather avoid that, just because it seems like it might not be necessary. I mean, so, and also they always use this H, and H is, well, so they say that like you look at end, so they look at endomorphisms of X. So they're identifying X with X dual. And then they say, we want ones that are self-adjoint or preserved by some star operation.
Yes.
So that's the sort of thing that you'd expect for like a Hermitian form. It's like,
Yes.
but for this, but if you think in terms more of the anti-symmetric part, there should be some description that it's like skew
Yes.
symmetric. And they don't really quite come out and say it that way because they don't talk in terms of A at that stage of the game.
Uh-huh.
So I'm just sort of hoping that like I can unravel some of the
Sure.
stuff and simplify it out. I'm sure that probably like the way the reason they went the way they went is that it then lets you like do a bunch of calculations that are good.
Yes.
But it would be nice to see like a more primitive story lying underneath that story.
Yes, yes, yes. I mean, there's still, again, I'm so far behind schedule and doing things, but there's a lot of special examples that I'd like to try applying all of this stuff to. Yeah. I mean, I want, I also really want to get into the, well, we've been getting into them, but I want to keep getting into the examples. But yeah, I just needed to, and still need to spend some time trying to straighten out this machinery so that I can apply it to the examples and know what the hell I'm doing. Yes, yes.
So anyway, that's what I wanted to tell you. And it's good that I told you, even though it's, or because I saw that like it sort of fell apart a little bit here and there at the end.
Yeah, we should keep trying to clarify it, but yes, this is good. All right, anything else that we should be doing now?
Nope, I don't think so.
Okay. So I'm still confused about, so I showed up late and then I don't know, I'll try to figure it out later. But usually we're supposed to try to stick to 4:30 to 6:30.
Yep.
Okay, I'll really try to stick to, I'll really try to show up on time next time, et cetera, et cetera, et cetera.
Yep. That doesn't sound convincing anymore. Apologize.
Well, yeah, I do have a whole bunch of good excuses that I was thinking on the way, on the way over, but no, I'm really going to try to do it.
Okay,
Okay, so thanks a lot.
Sure. Yep. See you.
Okay, bye.
Bye.